In this question 1b of tutorial 5a, we are asked the possible region of convergence shaped. What does region of convergence mean? In the Z transform, for different values of Z, this infinite series may converge or may not converge. The regions of Z which make this series converge is called the regions of convergence. XZ is only valid in the region of convergence. In the region that is not in the ROC, this sum will go to infinity or negative infinity, which does not mean anything of value to us. So we can only operate when this infinite series converges to some value. The possible ROC shapes are these 6 shapes, and these 6 shapes is dependent on the different values of xn. The xn, the sequence xn, can be causal, meaning it exists on the right hand side, meaning n greater equals to 0 only for x of n is not equals to 0. N less than 0 implying x of n equals to 0. So causal means that the signal only exists on the right hand side of the time axis or the discrete time axis. Anti-causal means that it exists only on the left hand side. It exists only for time n less than 1, less than 2, and so on. Double-sided means that it is both left side and right side. There's another category we need to denote the sequence by, which is whether it is of finite duration or infinite duration. So in the following points, we list down what does the shape of the ROC look like when the sequence is causal and infinite. In this particular case, when the sequence is causal and infinite, the ROC is outside the unit circle. So this is this guy over here. This is the typical case we are interested in. The sequence is causal and infinite. So I'll give you a causal sequence now. 0, 1, 2, and then it lasts forever for n. So this xn, for example, is 1/2 to the power of n un. Un making it causal, and then half to the power of n for positive all values of n will be some value not equals to 0. So that's why the ... is there. So this is 1, this is half, and this is 1/4, and so on and so forth. In this particular case, when we have such a sequence which is causal and infinite, the region of convergence is outside the unit circle, and if you refer to the lecture notes, there will be a pole sitting somewhere either here or here to mark the start of the region of convergence. When the sequence is anti-causal and infinite, the ROC is inside the unit circle. So now I'll shade it with green. Here, this is inside the unit circle. And here, again, the start of the ROC is always been marked by a pole. Because the sequence is anti-causal, the ROC is inside the unit circle. We'll discuss why later on in other questions, but here we are just stating the different types of sequence and the different types of ROC. Now let's have a simple case where the sequence is finite. When the sequence is finite, the ROC is everywhere except origin or infinity. So we are here at everywhere. So this is the typical ROC for finite sequence. So let's give an example. When xn is 1 and 2, then the Z transform of sequence 1 and 2 for index n equals to 0 and 1 is simply 1 converted to 1. 2 is 2 times Z minus 1. We then cast the polynomial into positive powers of z. So basically multiplying top and bottom by z. So we have z plus 2 divided by z. You'll realize that when z is equals to 0, then x of z becomes infinite when z is equals to 0. So there is a pole at z equals to 0. What about the zeros? When z is equals to minus 2, x of z becomes 0. So there is a 0 at x equals to minus 2. The ROC, when we sketch the ROC, is interested only in the pole location. So therefore, the pole, which is at the origin, then we will put a pole here, and we'll see that only at this pole position there is no ROC. Everything external to the pole is the ROC. So this example is for finite sequence ROC. So typically we are only interested in these 3 examples. Lastly, for the 4th example, when we have 2 circles, is because we have 2 infinite sequence. One for causal and another one the anti-causal part. And in this particular case, the red sequence here will have a ROC external to a pole, and for the green guy, the ROC is internal to the pole. And if these 2 poles, one of them is here, one of them is outside, allows the region of convergence to intersect with each other, it forms this annulus ring, and therefore the Z transform exists. If the intersection is an empty set, then the Z transform does not exist. This is a summary of the ROC. Thank you.